All right. So,
so sorry, overslept. Guess what?
I have.
And you wake me up. I missed my first 3 classes. Good read, you said. You never gonna show your face at school
Can
again.
you turn off your microphone if you're listening to somebody else?
I kill them if they want to live dead.
It's okay. You kill someone. Right. I made changes to calendar. Please go and look at the calendar. So we are going to have a test on 21st week from now, and we're going to have review next Wednesday, and we're going to go look at the questions and help you out with getting ready for the test one. Okay. How many of you know that the Zoom meetings are on here? If you miss a day or whatever reason that you had to leave or something, you can come back and watch. I put a 6th class meeting. Today is the 6th class meeting, but I do a class before, so I decided to put that in advance, people to catch up. I'm going to go over a little bit of 6th class period now. Basically, I'm going to finish the last class period, which is going to be 7th class period before the test, last class period. Can you see my screen now?
Yes.
Yes, sir.
Okay. I want to make sure that when I talk to you, if you cannot see the screen, I'm talking to the screen about the screen, and if you couldn't see, that will be bad. I'm going to go to the PowerPoint slides now from here on. I need to move out of the screen share. Then I had to go back to my screen share to get my PowerPoint. All right. We already talked about these molecular compounds, naming using prefixes. I want to make sure that it's being recorded. How many of you remember that I asked you to name molecular compound using prefixes? Okay. We are going to go, I think we go beyond that, but I'm going to go through it a little bit faster. We talk about compounds, molecular compounds have, any chemical compound has, some of them have their common names. So we have to know some of that. There are 6 pollutants, 4 in here. We talked about them. And the other 2 are there, lead and particulate matter. Particulate matter is solid particles or liquid droplets. Right now with wildfires in California, there are a lot of hazards caused by wildfire emission of particulate matter, dust particles, soot. Soot is a carbon particle coming out of burning, like that. We also talk about the risk of pollutants. It's toxicity of a pollutant and the exposure time, amount of substance encountered. So it not only the toxicity, duration of exposure is important. Anything could be poisonous in large quantities and large exposure time, but what makes something not risky is the small quantities and brief exposure times. So this slide shows you how the exposure time, the concentration of the different pollutants, 6 pollutants we talked about, and their exposure time, concentration in ppm and micrograms per cubic meter. I think we talked about this. So we summarize based on the ppm values, the low concentration values means toxic substances, and they have their average exposure time also smaller. This is the average level of air pollutants in the published by United States EPA. So significant reduction of lead. That 2 peaks are lead emissions. Since 2003, they declined dramatically after we avoid using lead compounds in gasoline. The gasoline was called lead unleaded now. Before it's not unleaded. So now because of that. But still we have a problem with lead because of underground pipe and smelting of lead to produce car batteries and things like that. That add significant amount of lead, and we need to be careful. So air quality data for US metropolitan areas shows.
Hello?
Yes.
I'm Chasten Moore from before we talked on the phone. We talked on the phone with the secretary before.
Oh, okay. I'm glad you are here.
Okay. May I ask where we are in the notes?
Are you in the can you see this right now?
I can see you move the icon with your mouse. I see you moving it.
Do you see a US map right now here?
Yes, I see a U.S. map, and it also says these words. It is established there are more than.
Yeah. Okay. Let me answer your question before I go further. Okay.
Okay.
I am on slide view right now.
Yes, sir.
But you just logged in. You don't know the course structure.
Oh no, no. I have the password and the thing, so So these are all the stuff that's on there.
Yeah.
Since I just finished registration, so what would you want me to focus more on instead of just? Do you want me to go back and do the rest of them, or do you?
Watch all the videos. Okay.
Okay.
And go through the course structure.
Okay, I will do is all the.
For example, since you asked me this question, okay?
Yes, sir.
Where do I see that? What you are talking about, okay? This is PowerPoint slides 2, okay?
Yes, sir.
So if you go there, so you're trying to catch up quicker, huh?
Yeah, I'm gonna try to catch up with work and my assignments.
Yeah. So ARV breathe. This is the one I've gone over before.
Okay.
We gone over in class videos, okay?
Yes, sir.
Okay, if you go here, molecular compounds, and you have access to this and my videos, okay?
Yes, sir. I have access to it now. My campus is fixed, so I can't go do this stuff now.
Okay, that's what I showed you, right?
Oh yeah, I remember this.
Okay, then now you know where you find them, right?
Yes, sir.
Okay, I'm going to go back to where I stop, okay?
Yes, sir. I
You
will
had to,
I will mute myself so I can listen to you.
oh yeah, okay. Can you see the map now?
Yes, sir.
Okay, now this map shows 10-day and during the 2015 and 16 air quality of different metropolitan areas. They are significantly higher in Los Angeles area. It's low in rural areas. There are less pollution, less burning of coal and industrial emissions, and vehicular emissions are less, okay? So you can see that air quality data are published by EPA for us to get an idea about quality of air we breathe. So you go through these slides, previous slide, like that one, and check which one has gone down significantly. There's 6 pollutants from 2000 to 2015. So that's what your turn to get familiar with the data. Now, EPA also have come up with the one called air quality index, because it's difficult for average people to understand ppm level of 6 different air pollutants. So they come up with the index called AQI, or air quality index, so that people in a metropolitan area have a good idea that whether the air they breathe is safe. This quality index have scales, 50 scale, 0 to 50, 50 to 100, like that, until 500. As it goes about 200, it's increased by 100 and 200. Okay, so anything air quality index forecasted for less than 50 is a good green, and moderate is yellow, and unhealthy is 100 to 150. Extremely unhealthy for everybody is red. Very unhealthy. You have to get out of the area. Hazardous is you shouldn't be staying there at all. So that's a air quality index is shown here. So this slide also shows air quality index of different substances. It depends on, mostly some areas have ozone mostly, or particulate. PM is particles, particulate matter. 10 is large particles, 10 microns. 2.5 is smaller particles. Smaller particles cause more damage to lungs and get in the bloodstream, and they can carry poisonous material on their surface, absorb on their surface. So that's for certain area in Washington from August 21 to August 24th. So you can see that how that volcanic eruption or fires can cause changes in the air quality index. So this one is during a period of extensive wildfire. So that period, it got worse on a 23rd, and it got a little better after 24th. So air quality index, you can watch the videos in the link below on your PowerPoint slides. So air quality index during regional events like what happened in Washington. In Northern California, there was right now wildfires going on. When the wildfire goes on, particulate matter is highest, extremely hazardous to breathing. So people have to get out of certain areas, smoke and particulate matter. So this shows how it changed from November 8th to November 25th, and gradually cleared off if you look at the change in pattern. It got back to normal after 17th, 20th, 21st. So these are important idea about air quality index, how we manage our pollutant. So we are going to talk more about chemical reactions. Chemical reaction is a reaction between two or more substances to produce new substances. For example, this carbon burning oxygen produce carbon dioxide. The molecular wave is at the bottom. Molecular wave is something that we chemists used to describe the process. Normally things take place in macroscopic view, like coal burning or coal burning on the top. But you don't explain anything, just the burning of coal. But this particular view gives some idea about the chemical reaction that takes place in the macroscopic view. So normally in a chemical reaction, we talk about law of conservation of mass. That means atoms are neither created nor destroyed. Therefore, before and after, the masses of substances are same. We did that in chapter 1 introduction. If you go back, watch them again, so you will get more information about conservation of mass. How does carbon react with oxygen? It's the combustion reaction. Normally, carbon in coal is in the form of graphite. Hexagonal carbon atoms in the solid, they burn with carbon dioxide, oxygen to produce carbon dioxide. There are two reactions that can take place. First one is with plenty of oxygen, they all can get converted to carbon dioxide. Limited supply of oxygen, the second reaction. So carbon get converted to carbon monoxide. You can see that more carbon is left on complete burning with this amount of oxygen, and more carbon left, less carbon left when limited supply of air, oxygen. Now, we in the atomic view, we describe these reactions as these are reactants, their products are the carbon dioxide and the carbon monoxide. And we also use the idea we're going to talk about later, limiting reactant. So this one describes it in detail, same slide with the description of pictures in the middle. I wanted to remind you, like, if you are here, can you send me an email on the chat box? Not email, your name in the chat box, so that I can keep track of who are here today. 7 people here. The one I spoke to, Moore, is that your name? Hello?
Yes, Chasten Moore is my name.
Yeah. So Chasten, do you know how to send a?
I sent an email to you.
No, go to the chat box.
I did. I sent it in.
Ah, okay, that's good. So since you are new here, I want to make sure that you, I have told others before. So
Okay.
we were looking at reactions. Balancing chemical equation in the molecular view is the chemical equation is the molecular view, atomic and molecular view. Balancing is important because we have to follow conservation of mass in a chemical reaction. The number of atoms on the product side, reactant side should be equal to number of atoms on the product side. Okay? How we balance chemical equation is we start with the one compound that is present in each side and balance the one element in that compound. So if free elements like oxygen is present, we balance it less. If you have units of atom like carbonate ion, sulfate ion, we balance as a unit, polyatomic ions as a unit. When we think it's balanced, we have to check the number of atoms on both sides, whether they are equal. So you can watch the videos on balancing equations and chemical equations given below, all right? Chemical equation, atoms are always conserved. Number of atoms on the reactant side is equal to number of atoms in the product side, elements, I mean. In a chemical reaction, the number of atoms in the group, in the molecule, is a number of atoms in a molecule is called, may be different, carbon dioxide, carbon monoxide. So we also show in the chemical equation using simple case S, L, G, physical state of the reactant, like solid, liquid, gas. So sometimes we don't show it, but most of the time we show changes in physical state. Okay, example. Methane burns in oxygen to produce carbon dioxide and water. This reaction is not balanced because hydrogen is not balanced. Hydrogen atoms on the reactant side, 4 on the product side and 2 on the reactant side. So we had to balance that. So we multiply by a coefficient in front of water, coefficient of 2 to make them equal. Now the hydrogens are balanced. Then when we go to the element, carbon side is already balanced. Then we go to the element, like we go last to the element present in one of the sites, one of the sites of the chemical reaction. So to balance oxygen, we count the number of oxygen on the product side. 2 from carbon dioxide, 2 from oxygen, 4. Then we put a 2 in front of oxygen, then it's balanced. So now you count again, then you got it balanced. So did you see how I balance chemical equations? All right.
Yes.
Okay, good. Propane gas is C3H8. Propane gas tank gas propane. It's a combustion reaction with oxygen produce carbon dioxide and water. Now to balance that equation, we start with hydrogen just like the previous one. There are 8 hydrogens on product side and 2 hydrogen on the reactant side. So we multiply coefficient, stoichiometric coefficients of 4 the water molecules, 4 in front of water molecules. That balances 8 hydrogen, 8 hydrogen. Now carbon is balanced, not balanced. So C3, we have to put a 3 in front of carbon to balance the carbon. Then we check the oxygen. Oxygens are 3 times 2 is 6 plus 4 is 10 oxygen on the product side. Therefore, oxygens, to balance the oxygen, we put a 5 in front of oxygen. So when you count the balance atoms, each element in the product side and each element atom in the reactant side, we see their balance. The limiting reagent is usually consumed during the reaction. Now, limiting reaction is a reactant is a idea. Like if you have 8 hamburger buns, 8 hamburger buns, and only 2 beef patties. In that case, you can only make 2 hamburgers, even though you have 8 buns. Do you understand my explanation? If you have 8 hamburger buns and 2 patties, you can only make 2 hamburgers because hamburger, each one needs 1 beef patty. So limiting reactant, limiting ingredient in that case is beef patties. So that just like that in a chemical reaction, there's a certain ratio mixing up. Depending on one in less amount, it limits the reactant. Do you understand that idea now? In chemical reaction, the maximum amount of product you can get is limited by whatever the ingredient or reactant is in limited supply. We're going to turn into this idea later. So balance these equations. hydrogen plus oxygen go into water. The water is not balanced. Hydrogen is not balanced, and oxygen is not balanced. We start with hydrogen. You can start with anything, oxygen or hydrogen. So we put a hydrogen, 4 hydrogens. We make it equal to 4 hydrogens on water. Then it's balanced. NO2 and nitrogen and oxygen go into nitrogen dioxide. Do you understand this? Same way we start with nitrogen. We balance nitrogen with a 2 in front of NO2, then balance the oxygen on both sides, 4. Okay, that's how we find the equation is balanced. Now we're going to talk about this more later, but in macroscopic scale, that's the large amount of. In a lab, you are not picking up molecules and doing the reaction. You're picking up something in the beaker or test tube that you can see. That's a large quantity of atoms. So we have an idea that to count atoms, we use the idea of mole. Mole is a mass taken in atomic weight of a substance, taken in grams, is equal to 1 mole of carbon. Mole is how many carbon atoms, how many grams of carbon atom. 12.01, that's in the periodic table that you have that mass. So if you have carbon atoms, we know there are 12.01 grams of carbon atom, there's a 1 mole. So even though we calculate material by grams, doing the molecular view, using the reaction, we have to do in moles, not moles our like a dozens of eggs. We use everything is multiplied by 10 to the 16, 6.02, 10 to the 23. That's the Avogadro numbers material. This 1 mole is a number called Avogadro number. It's a large number that makes us do chemical reactions in macro scale, large scale, but we still keep the count of atoms, all right? Carbon dioxide mole. How do you find the how do you get 1 mole of carbon dioxide? You get formula mass of carbon dioxide. Carbon is 12, oxygen is 16. We added up all 3. 12 plus 16 plus 16 is 44. 44 grams of carbon dioxide is a 1 mole. Water is 18. Formula mass is water is 18. 18 grams of water is 1 mole of water. So this Avogadro's number is an easy way for us to work with different reactions to manageable size. The molar ratio is given in a compound AB. That's the subscript of ratio is X to Y for AB. The carbon dioxide molar ratio is 1 to 2. Carbon dioxide 1 to 2. Molar ratios between reactants in a molecule, reactant molecules in a chemical reaction is their stoichiometric coefficients. Like water is produced from hydrogen to hydrogen, oxygen to produce 2 water molecules. That's the molar ratio. That's 2 to 1 to 2. So molar ratio is the one we use in stoichiometry. Stoichiometry is a name for chemical calculations. Calculations of amount of product you get from reacting to reactant. So this molar ratio is used to do the conversion to moles. For example, there's an equation here, A plus B going to C and plus D. So first you have the mass of A, that's where we go get a beaker of material in grams, water grams. We weigh them on a balance. And before we do the reaction, we have to convert them to moles. To convert mass to moles, we divided mole of A, that's X, divided by molar mass, get the moles of B, A. Mass of B divided by, that's not the X, they happen to put the same number, X here. That's unknown quantity. Mass of B divided by molar mass of B, mass of C divided by molar mass C, like that. You get the moles of A, moles of B, moles of C, and moles of D. So to convert, if you start with 1 mole of A, how many moles of C you get? A to C. You divide A by mass moles of A and multiplied by moles of C, you get the moles of C. So we're going to do this in detail. Again, we are just introducing the idea. During the chemical reaction, you have to convert it to moles before you do the calculation. So then once you get moles of C, then moles of C, if you, in this problem, you calculate the moles of B. And molar mass multiplied by molar mass, you get the grams of B. This is how you do a conversion in the stoichiometry. Moles, grams to moles, moles to the moles of other things, then get back to moles of the final product. So limiting reactant is the one that in this side we talking about limiting reactant. For example, there are on the A and B, the correct representation for the sulfur and oxygen is the A, picture A on the left side. B is not right because we don't find atomic oxygen as reactants. As reactants, we find diatomic oxygen. And sulfur is present as S8 molecules, S8 allotropes. On the first paragraph, we talk about this. Predict the product, either sulfur dioxide and sulfur trioxide. So I put in a molecular view, sulfur trioxide is on the top, sulfur dioxide in the top reaction, sulfur trioxide is in the bottom reaction. You can see more, in both cases, limiting is oxygen. In the first one, sulfur S8 to SO2, all the oxygens were gone. Left over is some sulfur atoms. So in the second one, both sulfur and oxygen, because the molar ratio S to oxygen here is not 24 oxygens, are not present, then both act as a limiting reactant, only two molecules. Would all the oxygen atoms react completely with all sulfur atoms? No. How did you arrive? You look at the molecular view, there are sulfur atoms left over. True or false? After the reaction goes to completion, unreacted sulfur atoms are left over. True. What evidence supports your answer? Evidence is molar ratio of the reacting materials. When converted to product, the oxygen is used up, so leftover is sulfur. So oxygen is the limiting reactant in this case. Do you have any questions? So sometimes when you burn hydrocarbons, octane here, octane is one of the components of gasoline. You can burn them in plenty of oxygen, 25 oxygen molecules, and burn everything to carbon dioxide. But if you run your car in a garage, closed space, you produce more carbon monoxide. How many of you heard about limited supply of air in your closed space? Even a gas cooker within indoor space could cause sometimes carbon monoxide poisoning if enough ventilation is not there. So incomplete combustion cause problems. Now vehicular emissions, your car has a catalytic converter, and the engine also has to be properly functioning. Vehicle emission reports look at how many grams of gasoline is burned when you run your engine for a certain period of time. Then they look at the carbon monoxide, and the third one is carbon, I cannot see, nitrogen oxide and carbon monoxide, nitrogen oxides, and the last one is carbon dioxide, nitrogen oxides, last one is carbon dioxide. Okay, grams of gasoline, carbon monoxide grams, nitrogen oxide grams, third one. Fourth one is carbon dioxide grams. So if you look at that, green line is emission standard force. The emission standard. So for gasoline, carbon monoxide and nitrogen oxides, there's a line. There's no green line for carbon dioxide, because carbon dioxide is not a problematic gas. It's not a pollutant that causes a lot of lung damage, or lung itself exhale carbon dioxide, right? There's no green line. So mainly three exhaust report, three substances are measured. So you can find out whether your vehicle is properly functioning with the engine and the catalytic converter. There could be problems. Then they ask you to fix them. The particulate emissions are given in this diagram. It shows air quality standards for shown in the map, that January 1st, 2016. The green means good air quality throughout the particulate air quality. But if you look at certain areas in the west, they are in yellow. So the air quality indexes for different things, particulate matter, ozone, are published by EPA. So you can go and look at them if you are interested in. Now there's a problem. One of the pollutants in the air is sulfur dioxide. Sulfur dioxide and sulfur trioxide, sulfur oxides we call it. How do you get sulfurs into air? What are the main source of emission of sulfur? Both gasoline and coal and burning wood cause certain amount of sulfur dioxide and sulfur trioxide. There are sulfur compounds in the source. Mostly is present in coal. Coal has significant amount of sulfur. So we have to clean the coal. Clean technology is called clean coal technology to remove sulfur. We used to burn sulfur directly without cleaning in the coal. So we had emissions and acid rains and all that. Sulfur trioxide is produced from sulfur dioxide ultimately with oxygen. If you have sulfur dioxide, it's converted to sulfur trioxide in the air. Then it reacts with water and produces sulfuric acid. It's a highly acidic substance. Good news, since 1985, we have seen a 55% reduction in sulfur emission in the US. How does that happen? Cleaning the coal before burning. So clean coal technology allows us to clean it up. Nitrogen oxides are also produced by gasoline mainly. Gasoline has nitrogen compounds that produce nitric oxide, nitrogen monoxide, and nitrogen monoxide react with the, like sulfur trioxide is produced, nitrogen dioxide is produced. In a car, this is possible because higher temperature of the vehicular temperature of the combustion engine. So like sulfur trioxide, you produce HNO3, nitric acid. It causes a lot more damage than sulfur dioxide, sulfuric acid. So the volatile organic compounds, when you burn them, also produce sulfur, nitrogen oxides. So nitrogen oxides are also cause secondary air pollution. Nitrogen dioxide react with oxygen. I'm going to show you in a minute how it produces ozone. The ozone is one of the pollutants, 6 pollutants that are harmful. Catalytic converters reduce CO by converting into carbon dioxide, NO, nitrogen oxide, both nitrogen monoxide and nitrogen dioxide, reduce to nitrogen and oxygen. Carbon dioxide, nitrogen, and oxygen are not harmful for our health. The catalytic converter is very important. Catalytic converters use rare earth metals, platinum and rhodium, and you must have seen your catalytic converter in the belly of the car. The nitrogen dioxide produce secondary pollutant we call ozone. Sunlight break it up to a nitrogen monoxide and atomic oxygen. Atomic oxygen combined with oxygen molecules to produce ozone. So when we have vehicular pollution, there's a purple color is associated with nitrogen oxide. The smog, particulate matter, cause the atmosphere to have low visibility. And purple color, that smog color has a distinct color. And ozone levels are very high when you have nitrogen oxide. Therefore, it's unhealthy in a metropolitan area with a lot of vehicles running during the peak hours. So this shows that vehicular emission ozone levels, how they change during the hours between starting from early morning to the late at night. Start with lower, then it grew up around 12 o'clock is maximum. No, it increased. Then around 8 o'clock, 5 to 8, it is red between 5 and 8. Then it reduced in the night. That's mainly because there are fewer cars at night. So indoor pollution is caused by sick building. The building is sick when it doesn't breathe. What do you mean by breathe? There has to be a ventilation system that sucks out contaminated air in the building, and there have to be fans like your AC system. Constantly pull out the air from outside to inside. That's a good thing. But if you have a sick building which doesn't breathe, a healthy building has kind of a fan system and ventilation system. So it causes carbon monoxide and volatile compound, volatile organic compound, some paint substances, some furniture has certain chemicals, so it can cause problems. Is there a sustainable way forward to keep the air quality? I think we have to make decisions for everybody, because if you leave it to industry, which is based on profit only, profit margins, they're not going to cut the emissions. They're only interested in making more money. So we have to come up with programs that EPA and American Chemical Society has for green chemistry. A green chemistry is chemistry that uses less energy, there's less pollution, create less waste, so therefore conserve, fewer resources are conserved, and they use fewer resources, use renewable resources, recycling. Right. How many of you remember we talked about the urban mining for cell phones? So something like that, renewable resources. That you read on you watch the video on 12 principles of green chemistry. So we done with the chapter 2, okay? So I'm going to, you have any questions?
Yes, I do about the I'm just not seeing those quizzes that's in the modules that's due soon. We have to do those, correct?
Say that again, I didn't hear it completely.
It's some quizzes that's in the modules that's due like September. I think it's September 26th or something like that.
Okay, let me go there, okay?
Okay.
I know you guys get antsy when you see something on the, say, it's due or something, right?
Yes.
I understand totally. Okay, hold on a second. I go back to my web page where here. Oh, I'm sorry, it's not that one. Hold on a second. I miss. I had to go back to web pages. Okay, now I share. Hang on a second, I'm there almost. Okay, in this one. Okay. Okay, let me go to Canvas quickly, okay? I must have came out of this 136. Okay, I had to go to student view. Okay, on the side, can you see something?
Yes.
Okay, about that. Only quiz 0, quiz chapter 0, okay?
Mm-hmm.
And quiz 1 and 2 are due, okay? There are 3 things you need to do.
Okay.
We go by, for each module is chapter 1 and 2 right now, right? So 3 quizzes and GER survey, okay?
Mm-hmm.
All right, I'm glad you asked me that, because sometimes they don't show clearly, what you need to be doing. They're listing out everything, okay?
Okay.
Okay. You guys have any other question?
Nope,
Let
not
me,
me. I'm good.
okay. I'm going to stop recording and I will see you on next Wednesday, right?
This Wednesday coming up?
Yeah, coming up.
Okay.
We're going to go review, okay, for chapter 1 and 2.
Okay.
So you guys prepare for